if my thread blocks were each 9 threads, 11 thread blocks give me 99 threads. I'm going to need 12 thread blocks to do this problem. 12 nines is 108. So in the last thread block, I don't want to double the values because otherwise I'll have gone outside the bounds of the array. So, you know, this again is a typical pattern you see. So when I launch this kernel, this is where I tell it how many threads should I use to do this calculation. But I don't tell it how many threads to use. I tell it how many threads should there be in a block, which is this NTPB, and how many blocks should I use. And here, because each thread is going to process one element of the array, the number of thread blocks is given by the total number of elements divided by the number of threads in each thread block, but I need to make sure I round up if it isn't an exact division. And so that's what a typical CUDA kernel looks like. Now, from the point of view of somebody who's never done GPU programming and it doesn't like CUDA and hasn't done CUDA, you're having to do a lot of stuff here yourself. Data movements, choosing the number of threads, even when it wasn't really important what the number of threads was. Yes, I could vary it to tune things, but why do I have to tell it? Couldn't it make some sort of decision? So with CUDA, you do a lot of low-level stuff, you know, managing memory, managing synchronization. You have to write all of this explicitly. In some cases, doing this does give you the performance. In other cases, you're doing a lot of work that you didn't need to do. So I'm not saying CUDA is bad. I'm just saying that you write a lot of stuff in CUDA that you maybe aren't used to having to do when you write for the CPU. So what is the complication in all of this? Well, this SMX is really like a vector processor. And when I say that I've got all these threads in a thread block, they don't all execute independently. They execute in groups of 32. And you always have to think of everything happening in groups of 32 threads, because they are doing the same thing at the same time. In particular, you need to make sure that when you access memory, what you would ideally like to do is, when you load memory, memory is loaded in blocks. And when 32 threads that are your vector unit, you really want them to use the minimum number of loads and stores from memory. So what you want is you would like neighboring threads should be processing neighboring array elements. If you don't do that, if you have a strided access, you'll need more loads. You know, if you have 32 threads processing sequential memory elements, in the best case, one vector load of 32 pieces of data in one instruction provides you the data you require for all those threads to execute. If those 32 threads are processing array elements with a stride of 2, then you'll need to do 2 loads to load 64 memory elements to provide the data for 32 threads to execute the next instruction. And these memory loads are expensive. So they call this coalescing. But what this isn't explicit in CUDA, but it's crucial for good performance. It doesn't matter what programming model you're doing. But basically what it comes down to is you want to vectorize your inner loops. And your inner loops should be the ones that are moving over the fastest array index. So what does this mean? You need a lot of parallel tasks, a lot of loop iterations for the GPU. Because each parallel task is basically going to map to a thread in a thread block. And you need loads and loads of threads to hide memory latency. There might be 3,000 odd single precision cores on the GPU or 1,000 odd double precision cores. But if you just have that number of threads, you'll get terrible performance. You need tens of thousands, possibly 1 million threads for the GPU to be able to swap these in and out to get the best performance overall. So you need lots of loop iterations. Now, OpenACC is particularly targeted at loop-based codes. But of course, science and engineering codes are typically loop-based anyway. So this is good. Your inner loops must vectorize, and they must have a vector length of at least 32. If that does not happen, you will get bad performance on the CPU. On the GPU. So vectorization is really important, and the vector length is longer than you see on the CPU. If statements inside the inner loop are allowed, but because of the way the code executes, they can start to harm performance. Every nested if statement is potentially doubling the number of instructions that have to be executed. So I wouldn't say never ever have an if statement in an inner loop. Anyone from NVIDIA, when I say this, throws their hands up in horror that you would do this. You should never do it. It will harm performance. But my view is, you're doing science. If you need an if statement and you cannot take the if statement out of the loop, what are you going to do? Change the laws of science? You know, maybe if you can find a better algorithm that avoids it, great. But if it's there, live with it. But if you've got 5 nested if statements, it's going to kill performance. It really is. So you've got to try and say, if at all possible, like you were saying, couldn't you just hoist, it doesn't have a J index, couldn't you take that mask statement outside the inner loop? If you can do that, do it. Use all the vectorization tricks from the old school manuals to do it. Memory should be accessed in the correct order, so make sure inner loops are indexing the fastest moving array indexes. That's good for the CPU, it's good for the GPU. And this comes back to this discussion we had this morning about arrays of structs and structs of arrays. Moving to having individual arrays for all the X components and all the Y components, all the Z components, is much better than having little structs which have X and Y and Z for one particle, followed by a struct for the next particle, because that will be strided in memory. Kernels are cheap to launch. I mean, in OpenMP, you have barriers, and you need that for synchronization. And in OpenMP, the usual goal is to make your parallel region as big as possible. If you've never done OpenMP, just ignore what I'm saying. But if you have, then that's you know that that's the sort of thing you try to do. For the GPU, launching a kernel is a very lightweight process. Yes, it might take 10 microseconds or whatever it takes, but you don't worry about it. So the way you get global synchronization is by launching separate kernels and synchronizing in between where you need to do it. Reduction operations, if you've ever tried to do a reduction in CUDA, it's a nightmare. You know, if you look at the CUDA SDK, they give about 6 different examples of different ways to implement a reduction with different levels of performance. And actually, on the new architectures, you might be better off using atomic operations anyway. So, you know, it's a very complicated process. But this is something that requires synchronization by the host. But the biggest thing is do not move data when you don't need to. You will need to port as much of the application as possible to the GPU, and you will probably have to port more than you thought you had to. Even things that take almost no time, you might be porting those to the GPU just because the data's on the GPU and you don't want to move it. So doubling the values of an array doesn't make sense if the data lives on the CPU, but if the data's already on the GPU, you just double the values, write a really simple kernel to do it, so the data remains on the CPU, on the GPU, sorry. So you will be porting things that you didn't think were important just to avoid that. Great, just do CUDA, why not? Why talk about a new programming model? Well, as you've seen by the CUDA example, CUDA is hard to write and debug. You write a lot more than you'd be writing if you're writing just straight CPU code. And you have to do all this memory management all by yourself. It's hard to optimize for a specific GPU. I didn't show any optimizations, but all these shared memory tricks and whatever, the reason there's 6 different examples of how to do a reduction is because there's lots of different optimization tricks for different architectures. And you might optimize for one GPU model, and then they upgrade to a new GPU model, and it just doesn't give you good performance. And if you want to port to a whole new accelerator, there's a lot of work. And then you've got a CUDA version of your code and a CPU version of your code, and you've got to keep these synchronized, you've got to keep them working. When somebody adds some new science, you've got to put it into both versions and so on. Directives are a way of getting around this because you take the original source code that runs on the CPU, which means you've got one source base, which is easier. If you've done OpenMP, you're quite used to parallelizing with directives. The compiler handles a lot of this repetitive coding, the CUDA mallocs, the CUDA mem copies, the CUDA frees. It does all of this for you. The compiler can make a default scheduling. It makes a default choice of the number of threads per block and all of how many thread blocks to use. If it's wrong, it's usually pretty good, but you can tune it, but you don't want to have to do that every time. You just want to tune it on a particular kernel where it's going to make a difference. Of course, it's a higher level programming thing. You don't have the same low level control. There might be performance sacrifice, but I would say, how many of you write your entire application in assembler? You should. You could get a factor of 2. But, I don't need to explain why you didn't make that decision. And the same for the GPU, Don't do low-level coding unless you need to. If assembler gives you good performance on the CPU, you don't write your whole code in assembler. You write a plug-in module for that particular routine. And the rest of it you leave in C or Fortran. And the same thing, if you really want that low-level control of CUDA and you can really benefit from it, you write OpenACC for the rest, where it doesn't matter, and then you plug some CUDA in for that particular operation. And there's interoperability to do that. So OpenACC, it's about a couple of years old now. It was drawn up by NVIDIA and Cray and PGI and CAPS. So there's multiple compilers, which is good for portability, it's good for debugging, it's good for the programming model surviving. C, C++, and Fortran. And GCC announced at Supercomputing that they are now starting to do some development to support OpenACC, targeting, I think, version 4.9, which is later this year for at least some coverage of this. So this was a slide that was put together for a grant proposal. One of the customers said, we're going to propose a proposal with OpenACC. Do you have any document describing the strategic risk factors of OpenACC? So, what are the questions you would ask? If I'm going to port to OpenACC, it's a new programming model. Should I do it or not? Is there any way to run my code? Well, of course there are. I mean, there are now XC30s and XK7s and other vendors, systems as well. What about the future? Well, OpenACC is a higher level programming model. It can be targeted not just at NVIDIA GPUs, and PGI and CAPS already provide support to target Intel Xeon Phi or AMD GPUs. The Cray compiler doesn't do it, mainly for the reason that we don't supply AMD GPUs. We only package NVIDIA GPUs, so that's been our emphasis. Will it continue? Well, of course, if we turn around and say to Oak Ridge or to CSCS, oh, OpenACC, no, we've got a new idea now. I'm sorry you've ported all your code. We can't do that. So, I mean, there's customer pressure to continue. But more than that, the OpenACC committee started with 4 partners, and we're now at 18 or so. And it's not just vendors. There's HPC centers and software developers as well, and tools partners. And so version 2 came out at Supercomputing in November, and now there's new version. They're now working on the next version, which could be a 2.1, it could be a 3.0. It just depends how the standardization process works. Will I do all this work and then I find I don't have to do it? Will the compiler do everything for me? Of course it will. Just like you've been told for the last 30 or 40 years, the compiler will do everything. The compiler will parallelize your code for you. But it never works. It never quite gets there. It's a very difficult problem because nobody knows what you want to do better than you do. And data locality adds to that challenge. The compilers certainly can help, and that's the goal of OpenACC, but it'll never remove the need for you entirely. So we're not taking your job away. If you're thinking about, why will they employ me if something could do it all for me? What about OpenMP Accelerator directives and OpenMP4? Good question, that. OpenMP4 has an accelerator directive model that's not a million miles away from OpenACC. OpenACC came out before the OpenMP Accelerator directives because we needed something kind of 2 years ago as opposed to just coming out now. The compiler support is very immature. So starting now, should you start with OpenMP4? No, because there's no compiler, no release compilers support it. 8.3 for the Cray compiler will have some support in it for the Accelerator directives. Not necessarily optimized yet, but it shouldn't be too bad because it's building on the OpenACC technology. But I would say the work you would do in OpenACC is not wasted because you spend more time thinking than you do coding. And that's the good thing about a high-level program model. The thinking is data locality. How does data move in my application call tree? Where should I put in the statements to make sure data doesn't move? This will translate into OpenMP Accelerator directives or any other programming model. So, if you're going to start the process, I would start with OpenACC. You can either stick with OpenACC. If you want to go to OpenMP4, as its compiler support comes in, do so. You can keep the OpenACC in as well. Have both sets of directives. If you want to transition entirely to OpenMP4, do so. OpenMP 4.0 does not have all the functionality that you get in OpenACC. It's the first version of the standard, standards evolve and they do it step by step. So there are things you can do with OpenACC that for an NVIDIA GPU will give you a good performance gain. But that's not to say it won't come in OpenMP 4.1, but that might be a year down the road. So, I'm not saying OpenMP 4 is useless because it isn't. What I'm saying is that there is a catching up process that's going to go on. So, I would start the thinking process now with OpenACC and then translate, which will be a fairly mechanical job. You could even think about writing a tool to just do it automatically for most of the code. But do that when the compilers are ready to really let you test it.
So, Alistair, what I think most users are hoping for is that OpenACC will somehow be incorporated into OpenMP long term. Is that something which Cray is trying to push? Or it seems like the two communities right now are a little bit antagonistic.
There is some antagonism. Cray, I think, would be very happy for OpenACC to be absorbed into OpenMP. I don't know what the view of the OpenMP committee is. I certainly know that there are some vendors who are not, if you said what is their statement about how they support OpenACC, depending on who you talk to, it might vary between we don't, it's not on the roadmap, or over our dead bodies. There is this, I don't think, OpenMP, the Pope does not bless particular standards bodies, A standards body basically lives or dies because it has community buy-in. And OpenMP is no more official than OpenACC. It's clearly more established and it's clearly a wider standardization body. And it would be good to do that, I would say. However, I don't think that that is necessary. The way of expressing things in OpenMP and OpenACC is slightly different. There are differences. Some of these are simply syntactic, but there are other things. But it's sufficiently close that you could do both. But could you do something that will OpenACC? I don't think you should wait on the basis that I'll wait until that happens. I think that would be a mistake. So will my code accelerate well with OpenACC? It should have loop nests, is basically the statement here. The loop nest should span as much code as possible. If you have a lot of serial code, that's not a good code for a GPU. Don't have too many if statements. Task-based is good as long as each task has a loop nest in it. Tasks can be good because you can get overlap. And yeah, so what does OpenACC actually look like? Well, just like OpenMP, you basically put comments into your code. And there are some API calls as well that I'm not really going to say very much about. For C, hash pragma ACC and then something. For Fortran, exclamation mark $ACC and then something. And then you often need an end statement, although in some cases these are optional. You can do fixed form, you can do freeform Fortran. In theory, that's all you should ever do. The same with OpenMP. But of course, it never quite works that way. And you'll always need slightly different code because you're calling API functions just like you do for OpenMP. Or you might need to do a particular recoding trick for the GPU that's not for the CPU, although often it is. So you need some sort of pre-processing. And so just like OpenMP, there is a macro defined that you can use for your pre-processing where you need it. But you should try and minimize the use of this, but it always happens. So as a first example of what an OpenACC code would look like, I'm going to double the values of an array. What do? I say this is a parallel loop, and that's it. What does the compiler do? The compiler analyzes the data dependencies in here, and it will understand that C is write-only, and it will understand that A and B are read-only, and it will sort out the CUDA mallocs, or the equivalent thereof, and the CUDA frees, and the CUDA mem copies at each side to only transfer the data that's required in the right direction. So if C is write-only, it will do a CUDA malloc, but no CUDA mem copy there, and it will do a CUDA free, but it will also have a CUDA mem copy to bring that data back, but it won't bring back A and B. The Cray compiler does not use intermediate CUDA. It is not really writing CUDA mem copy. I'm just using the language that was used before. It does these data transfers, but it does not have an intermediate CUDA. You cannot ask the compiler CUDA then hand optimize that. Does it get the data movements right? I mean, that's the big question. And the answer is yes. Data movements is a well understood problem, and the compilers are very good at it. And I have never seen a case where it's got it wrong. And that's honestly in all the time with the Cray compiler. What it does do sometimes, it does overkill. It sometimes isn't quite sure, because A and B are used later on, well, it wasn't quite sure whether it needed to bring them back and this sort of thing, especially for temporary arrays. It will sometimes do too much transfer, and then you have to use clauses to tweak that movement, to minimize it. You incorrect answers, and that's the main thing. It will also look at these loop elements, and it will divide these up into the threads that are going to execute on the GPU, and it will divide these into thread blocks in some appropriate manner to execute on the GPU. So it's doing all of that work of choosing a default number of threads per block. It's all done for you. OpenMP does a similar sort of thing. You know, you split up a loop nest with an OpenMP parallel directive. The difference is OpenMP, by default, will only split up the outer loop, whereas OpenACC will split up multiple loops in the loop nest. If you've done CUDA programming, you know about shared memory optimizations and all of these sorts of things. The compiler does this sort of caching for you. Again, you can go in and help it, but you don't have to do it all for it. There are two ways to say this loop nest should be divided up, parallel loop and kernels loop. And when you read the standard, it's very confusing as to why there's two. It's for historical reasons. They do have slightly different use cases, but I always use parallel loop. If you really want to know the difference, we can talk about it later. So let's double the values of an array. Since we've already shown you how to do it in CUDA, so what do? You say, well, here's my array. I mean, this is written in Fortran. It could have been written in C. But here's my array. I'll initialize it. So I'm going to initialize it on the GPU. And then I want to double the values, and I'll do that on the GPU. So I basically just say parallel loop, parallel loop. Because I've broken the parallel region here, there is a barrier. So I know that this will have finished before it starts doing that, because I don't want a race condition. So the code is still the same CPU code. If I switch off recognition of OpenACC directives, it will still compile and run on the CPU and give me the correct answer. Yep.
Does the OpenACC automatically determine whether it is performance-wise good to move a particular loop to the GPU and run it on the CPU? If not, if, for example, the mem copy, in this example, the mem copy would be more expensive than running the code on the CPU?
No. I mean, if you use, as you'll see, later in the course. I mean, if you use something like the Cray libsci, which can do BLAS operations on the GPU, if you provide it with data that's on the CPU, it will make a decision within the library as to whether to do it on the CPU or to move it to the GPU. But that's a hand-coded optimization within the library. You could write the same sort of decision tree in your code, but you would have to code that yourself. Sorry, you have a question? But, so there, the compiler has made all the decisions about what to do with the data. Now, codes process data. In a serial code, there's no complications, but in a parallel code, things are more complicated. Some data should be, whether you're doing OpenMP or OpenACC, some data is particular to a thread, the loop index, for instance. Other data is shared between all the threads. And you don't really want to have a separate copy of this array for every thread, because each thread is only going to process a portion of the array, and you just saturate your memory. So some array data you have to say is shared between all threads. And how do you kind of do all this? Well, you do this with something called data scoping. The compiler does some automatically, or the programmer can do some explicitly. If you don't get it right, you'll either have a code that's got far too much memory use, or you'll have a code that gives incorrect answers. And if you're going to do any OpenACC programming, you have to understand something about data scoping in the same way that if you want to do OpenMP programming. So data scoping means is a way of ensuring that we get the right answer whether we're running in parallel or serially. So we have to declare the variables in a parallel region, whether it's OpenMP or OpenACC, to be shared or private. Shared means all loop iterations process the same version of the variable. That variable could be a scalar or an array. Typically, it's an array. So in this example here, where I am doubling the values of an array with an intermediate temporary called T, A and B are shared arrays. The threads between them will process that single copy of the array. Private means each loop iteration will use its own copy of the variable. T is a private scalar. Loop indices are also private. First private is a variation on private. Let's not worry about that for this. And in OpenMP, that's exactly what you write. You declare these variables to be shared or private. In OpenACC, private is the same, but shared is more complicated. Shared is more complicated because as well as, okay, this data is shared between the threads on the GPU, but how did the data get to and from the GPU? Should it move or not? And then, so shared in OpenACC has to be split into 4 different cases. If we read and write the array, it should be copy. If we only read it, we only want to copy it in at the start. If we only write it, we only need to copy it out at the end. If it's a temporary array that's only used within the scratch space, then you don't want to do any data copies at all, and then you say create. And these are the names that they're given. I mean, so within a parallel region, scalars and loop index variables are private by default. You don't need to say they are. This is different to OpenMP. In OpenMP, loop indices are private by default, but scalars are not. So there's a difference with OpenMP if you've used it. Arrays are shared by default, and the compiler will make a decision, as I said, based on data movement as to whether it's copy in, copy out, or whatever. You can change all of this by using explicit clauses. If you like the approach, I don't want the compiler to do anything, I want to do everything myself. If you want to do that, you can use a default none clause, and then you have to do everything. And if you don't do it, the compiler will complain. So if I wanted to write it in explicitly, this example, A is write only here, so it's copy out. A is read write here, so it's copy. And I could put those clauses in, and it'd be exactly the same. But of course, the real problem here is not the fact that these kernels are oversimplified. It's the fact that the whole array is being moved back to the CPU here, and then is moved all the way back to the GPU to do the next kernel. And the PCI transfer is really slow. And so this data is sloshing from the GPU to the CPU every time I do a kernel. And that kills performance. So the other big ingredient of GPU, of OpenACC, is the concept of a data region. And the data regions are a way of allowing data to remain in the accelerator to be processed by multiple kernels with no data movements in between. The data regions that you write, so what you do in your code is you specify points in the code where data should move to the GPU and points in the code where data should move back to the CPU. So these data regions you put in are simply labels in the code. They can surround not only GPU kernels, they can also surround CPU serial code. So typically the way you use them is you have a data region that spans almost the entire call tree of your application. And within that you've got serial code executing on the CPU, MPI calls going here and there, and you've got GPU kernels being launched. Once you're inside the data region, the main array is living on the GPU. There is no synchronization going on automatically with the CPU. You've got a version of the data in GPU memory, you've got a version of the array in CPU memory. If you need to synchronize them, you have to do that yourself. The compiler does not do that for you. So the synchronization inside the data region is all up to you. So what do you do to make this data region? Well, there's a new directive which is ACC data and end data. With C and C++, instead of an end statement, you've got curly brackets. If you do real C++ programming, or you use an object-oriented type of Fortran programming, there's something called an unstructured data region, which I'm not going to talk about. For most procedural code, structured data regions are what you use. A data region only does what you tell it to do. If you say parallel loop for a loop nest, the compiler will do some automatic analysis for you to work out the data movements. And you can then change them if you want. If you just put a data region in and don't put any clauses about data movement, private, not private, not private, copy in, copy out, create, copy, the choices to specify how different arrays should move. If you don't say that, the compiler will do nothing automatically. It's just too difficult for it to do it. It doesn't know what you want to do because this is spanning a huge amount of code. So if you just put it in with no data clauses, nothing will happen. The code will run, but nothing will happen. So what would I do for this simple example? Well, what I want to do is only move data at the start and end of this program. The data will be initialized on the GPU. It will be modified on the GPU. So overall, from the point of view of this data region, because array A that I modified will only move on the boundaries of the data region. So from the point of view of the data region that spans these kernels, A is being used in a write-only fashion. So it's specified as copy out. Within this data region, at this point between these two directives, I could put some host serial code in. I could even do something to the copy of array A that is in CPU memory, which will then be overwritten at this point when the GPU data is transferred back. I could do this, just don't do it. It will hurt your head trying to debug that. But it is possible. There's no automatic synchronization. If at this point I needed to know about array A, or I wanted to print out a few values from the array for debugging, or if I needed to send the first and last values of array A on MPI, I might want to bring some of the data back to the CPU from the GPU, and there's a way to do that explicitly using a directive called update. So there is a mechanism. I'm not going to do much about it today, but there is a mechanism for synchronizing what you need to. So we've talked about parallel regions. Data regions you don't talk about private for data regions. It doesn't make sense. It's not a work-sharing directive. It's just a way of labeling data movements. There's no such thing as private for a data region. There is no automatic scoping. Don't expect to put a data region in. If you don't mention the array, the data region won't do anything with that array. And what will then happen, if you don't mention it, the arrays that you didn't mention will be individually moved at the boundaries of each kernel, just like that first example with no data region. How do I make sure that my parallel region knows that there's a data region and knows that the data should already be on the GPU and it shouldn't do any data copies? Well, if the data region is in the same routine as the parallel region, you don't need to do anything. The compiler just spots it. What if the routine is in a, what if the routine with the parallel directive, where the GPU kernel is down in the call tree and it's in a different source file and a different routine? How does it know that the data's on the GPU? Well, you have to tell it. And the way you tell it, so here we are again. We're going to double the values of the array again, but this time, the initialization kernel is on the CPU. The initialization kernel is in the main program, and it can see the data region. So I don't need to do anything. It will just know that A is on the GPU. But then I call in a new routine. This is a CPU call, and in that CPU routine, I'm going to launch a new kernel to double the values. There, I have to say, you should find this array on the GPU by using the present clause. And this is where all the thinking comes in, putting these data regions in. When you've got a complicated call tree, and you've got multiple code execution paths, trying to work out how data moves in the call tree to understand where should I put the data regions, which routines should I port to OpenACC, which can vary depending on the runtime input files and all these sorts of things. This is where all the thinking goes on. It doesn't matter if you're doing this in CUDA or OpenACC, the same thinking process has to go on. But the point with OpenACC is that you don't have to write all these mem copies and everything. You're just putting directives in. They're easier to write. The compiler writes the mem copies and things for you. You just give it a clause, a data clause. It gives you more time for thinking. And it gives you more time. It's easier to experiment and change stuff. Now, one thing, if you've done OpenMP, sometimes what you're doing is a reduction. What that means is that I'm going to combine values from lots of loop iterations together. I'm going to sum the values of an array, for instance. Or I'm going to find the maximum value of an array. And in this case, you need to make sure that you tell it that in this case here, I'm taking the maximum value of an array, and I'm also adding up the values of an array. Two different operations here. But they're both reduction operations. T and U are not completely private to the threads because I need to combine the values, but nor are they shared. They're what's called a reduction variable. And you need to tell the parallel loop directive that it has to be treated in this special way. And that's the same as in OpenMP. And you do it in the same way using a clause that's reduction, and then you need to tell it the sort of reduction that's being used. If you're just adding up, the reduction is plus. Actually, subtraction, the reduction is plus as well. There's no such thing as, well, and that's standard. If it's a maximum, you have to tell it that the reduction U is a reduction variable of class maximum, and that tells the compiler what to do. You can only do reduction of scalars and not of array elements. If this is a problem, maybe use a temporary scalar, but that's something in OpenACC. There are some differences between OpenACC and OpenMP. I'm not going to go into them too much, but if you're used to one model and you go to the other, you have to be careful or you get bitten. So in summary, you've got compute regions, these kernels, and there are directives to create those. The important thing after that is data regions to keep the data on the GPU. And you control these things with clauses. And you've got clauses to control the data scoping. So what's the rest of OpenACC for? It's all about performance tuning. But the point here is I haven't got time to talk about it, but you can successfully port a lot of code with only the knowledge that I've given you so far. So this example of the Himeno that you'll get in Practical 8, which is the same code you've been looking at in Practical 1, but with an OpenACC port, you can beat the full CPU with OpenMP parallelism across all the cores. You can beat it with the GPU only using the directives we talked about, which is great. I mean, that's a win. You know, that's, as a productivity thing, you know, a modest number of changes of code can give you this, stopping the data movement means that you can usually just beat the GPU. The Cray compiler, the PGI compiler, they're both pretty good at scheduling good stuff on the CPU. Cray says, you know, if you can write the same algorithm in CUDA and OpenACC, and you don't get 80% of the performance of CUDA using OpenACC, it's a performance bug, and tell us, because the compiler's obviously stupid, and we will correct it. In practice, 90% is what we see. In some cases, we beat the code. You know, we've got a smart compiler team that writes some really good reductions, for instance, so you better be very confident of your ability to write a reduction in CUDA to beat them. And, you know, we've had examples of that where people have come and said, but how did you do it? You know, I wrote, you know, I added 200 directives to my code. I had to write 10,000 lines of OpenCL to, and I just cannot get near the performance. I wrote, you know, 5,000 lines of CUDA, and I'm slower. So it does happen. I'm not saying it always happens, but there are real use cases where you've got to be better than the compiler developers to be confident that you can do better than the OpenACC. Some people can, but, you know, it's easy to think I'll slot in a CUDA kernel here and your code goes slower, even when you thought you'd written the CUDA pretty well. And, you know, I mean, within one of the projects that I've been working on, there's a code called NEC 5000, which is a big CFD application, and they ported this to run on GPUs, and it's run on 16,000 GPUs with MPI at Titan. And basically, it's got one directive per 1,000 lines of code to port the application on average. And there is some performance tuning in that. But, you know, in terms of rewriting the entire application in CUDA, which is what you'd have to do if you just went down the entire CUDA route, there's a big productivity win. And because of the interoperability, you can write a CUDA kernel and slot it into an OpenACC code without any data movements having to take place. And, you know, if you want to performance tune a particular kernel, but just do it for that kernel, don't do it for the whole thing, you're wasting your time. So, in the language of OpenACC 2, we have finished, so we are exiting the data region. Now, the clause that should go on here for you is copy out, or take the knowledge away, not delete, which would just deallocate the space. Are there any questions? Yes?
The size of the array is larger than the memory. Compiler will take care of it?
No, it won't work. The same as with CUDA. I mean, it won't try and split it up for you and do something clever like that. You are limited by the global memory of 6 gigabytes. I don't know of any. I think the thing to do would be to write a test case and look at it. But really, ideally, you want to keep your data on the GPU. Don't just port that one routine. Unless, I mean, a routine that's compute heavy for a small amount of data could be worth doing that way. But in general, try and get more of the call tree, more of the routines onto the GPU is a better approach. If you do have to do data transfers, what you need to do is you need to start doing them in the background, like that pipelining example for G2G. There is a mechanism in CUDA called streams. There's a mechanism in OpenACC called async handles. They're actually the same mechanism, it's just the two models address them differently. But it's a way of overlapping stuff, doing data transfers in the background. That's what you should try and do. So for some cases that could do, but I think really you have to benchmark what you're trying to do to understand what's happening. Yes?
So I'm really glad you brought up the example of modifying A on the host within the data statement. This is a problem which really arises very often. What would really help developers is to have some sort of mechanism, some sort of tool to tell you if things are out of sync, right? On the CPU and the GPU, host and device. Is there anything in the works to give us that?
Well, I think part of the problem is that things are implicitly out of sync because you basically create a data region and you create a copy of that array on the GPU. And in most cases, you're then thinking the CPU memory remains allocated, but you're never going to touch it.
Yeah, but all it needs is some sort of bit to determine whether the array has been modified or not, right, on the GPU. As soon as you modify it, then it's out of sync, right?
I don't know of anything to do that.
Couldn't this be done like as a compile type warning? Because the compiler would notice there is an assignment, for example, to a variable which has previously declared the copy or copy out for a data region which is dropping this assignment, and then if the CPU code has an assignment to this particular variable, the compiler would print out the warning.
You could see that working quite easily for Fortran, and the reason that things work quite easily for Fortran is because a Fortran array is a complicated little data object that includes information about size and shape and all this sort of thing. And that's why Fortran actually, for OpenACC, was much easier to implement, whereas an array in C is typically a pointer that contains no further information. So for Fortran, you could think of somehow, I mean, you might have to do this at runtime because you don't know the call tree exactly for your application, but you could set some sort of bit in the Fortran array descriptor, in the dope vector, that would somehow trip things. Potentially this could be done as a debug thing. I don't know of anything.
Just a suggestion for you guys, that would be a feature which I think would be very useful to developers.
But it mostly is going to be out of sync because you're not going to process the CPU version.
Right, but I mean, often then you think you've updated things on the host, and in reality you haven't. It's basically that. You're missing key updates. And you think you've done it, you think it should be updated, and in fact it's not updated. And that's where the errors often occur.
Okay. But I don't think this...
Just to mention your merging conversions. The merge gives you roughly, well, say a whole space code at a location where you didn't anticipate it, and you don't see it during merging.
Yeah, I can see a use case, yes. I don't think there is anything. I can ask what sort of thing there are, because, people they're interested in these sorts of suggestions. I mean, GPU, why? Don't want to do that. There are mechanisms in OpenACC. Essentially what you do in CUDA, where you just allocate space on the GPU and don't have space on the CPU. But the counter-argument to this is that typically, with current architectures, you would typically run with one rank per node. The CPU rank sees 32 gig. The GPU version sees 6 gig. So CPU memory is not the bottleneck. So, but there are ways to have fine control if you want to do it that way.